In this video, we're going to learn about Ohm's law and how to apply Ohm's law in solving electrical problems. Ohm's law states that the electric current through a conductor between 2 points is directly proportional to the voltage across the 2 points. So in practical terms, that means when you have a circuit with a component in it, a resistor, as the current is increased, the voltage will increase proportionally. And if you graph the potential difference versus the current, in this case, you would get a straight line. And one thing we need to keep in mind is the definition of resistance is the potential difference divided by the current. So what that means is, depending on which type of graph you have, you can calculate the resistance based on this graph. And so for a graph where V is on the y-axis and I is on the x-axis, the resistance is the slope of this line. So the slope is equal to the resistance. However, sometimes you can have graphs that look slightly different depending on the independent and dependent variable. So in this case, if I is on the y-axis and V is on the x-axis, then the resistance is equal to 1 over the slope, the inverse of the slope. So, most importantly thing to remember, for an ohmic object, the resistance remains constant, and the slope of a VI graph is the resistance of the object. Not all conductors obey Ohm's law. In a previous video, we learned about things like thermistors and light-dependent resistors, and they do not have a constant resistance, whereas an ohmic conductor will have a constant resistance as you change the current. Another example of a non-ohmic object would be a filament light bulb. These aren't used very commonly anymore, but the old filament light bulbs used to pass an electric current through this filament here, normally made of tungsten, and when the current would pass through it, it would increase the temperature. Kind of like the friction from the moving electric charge. This increases the resistance, and which would in turn increase the temperature again, and eventually it would get so hot that it would glow. So what's happening as the temperature is increasing, as the current is increasing, the resistance is increasing. And so resistance is not constant for a filament light bulb. The graph for a filament light bulb would probably look something like this, where as you increase the resistance, you see the slope of this line is changing. So the slope is increasing as you increase the current. In example 1 here, we have a battery provides 9 volts to the circuit. Determine the current in the circuit for a 95 ohm resistor. So it's a very simple circuit here, 1 resistor, 1 battery, it's providing 9 volts. And so what we can do is we can use that knowledge of the definition of the resistance, which is R is V over I, and we can use this to solve for the I. And so in this case, I is equal to V over R, which is 9 volts over 45 ohms, which gives us 0.2 amps. Here we have a VI graph for a resistor below, and we want to sketch the VI graph for a resistor with half the resistance. Now we're assuming that this is an ohmic resistor because it's a straight line. So if we wanted to do that, well, we know that the slope is the resistance of this resistor, so slope of this line. So half the resistance would be half the slope. So it would be somewhere like this. So this line here would represent something with half the resistance. Let's use this graph to determine the resistance of this component. So as I mentioned earlier, we want to check these out. And we see here, yeah, we have current on the y-axis. Not totally common to see that, but in this case we have it. And so what we want to do is find the slope of this graph first. And the slope of this graph, you want to take 2 points that are easy to read far away from each other and then calculate the slope that way. So the 2 points I'm going to select are this one here and this one here. So I can see that this is 5, 3, and this is 1 and 0.6. So if I use my slope formula, we get 3 minus 0.6 over 5 minus 1, which gives me a slope of 0.6. And because this is an IV graph, I know that the resistance is the inverse of the slope. So the resistance is going to be 1 over 0.6, which is 1.7 ohms. Which of the following graphs shows an object that increases in resistance as current is increased? And so right away we can eliminate this one here because a straight line indicates constant resistance. So the resistance is not increasing. if we look at this first one here, as the I is increasing, we see that the slope is going from, we have kind of a steep slope here, which would be a high resistance. And then this is a bit of a lower slope here. So we can see that resistance is going down. So it can't be this one. And by process of elimination, it must be this one. Also, we would know this because this is an IV graph. So the resistance is the inverse of the slope. So if we start with a high slope here, that means the resistance is low, and then a low slope here means resistance is higher. So this is the correct answer here. A copper wire of length 15 centimeter and radius 2.5 millimeters has a current of 38 milliamps passing through it. Determine the potential difference across the wire if the resistivity of copper is 1.7 times 10 to the negative 8 ohm meters. Now we have a lot going on here, and this is definitely one of those questions where we maybe want to start listing out some variables. So the first one we got is length. And length is 15 centimeters, so I'm going to convert that into meters. And then we have radius, which is 2.5 millimeters, so I'm going to convert that into meters as well. We have current, which is 38 milliamps, which I will also convert into amps. And then we have resistivity is 1.7 times 10 to the negative 8. And we are looking for the potential difference here. And so we have to figure out what's connecting all of this stuff and why do we have all this information. So looking at L, R, and rho here, that makes me think I can calculate the resistance. And then if I have the resistance and I have the current, then I can find the potential difference. So really what I need is this two-step problem here. I first want to find the resistance, then I'm going to find the potential difference. So if I start with the resistivity equation, of resistivity equaling RA over L, we see that we can rearrange this to solve for resistance, and so resistance is the resistivity times the length divided by the area. If I plug in the values that I need, I have 1.7 times 10 to the negative 8, a length of 0.15, and the area, because it's a radius, it's going to be a circle, so it's pi times 0.0025 squared, which gives me a resistance of 1.29 times 10 to the negative 4 ohms. From there, I can take the Ohm's law equation and calculate the potential difference. And so I can write it in the form V is equal to I times R, where I is 0.038, and we have 1.29 times 10 to the negative 4. And so we see we get a potential difference of 4.9 times 10 to the negative 6 volts. So this is an extremely low number. But that makes sense if we think about this is just a copper wire, and we use copper wires because they have such a low resistance, so they don't really take a lot of energy up in the circuit. But this is the process for doing that for a conductor. The following graph shows the relationship between potential difference in current for a resistor and a filament lamp. Which device has a larger resistance at 2 amps and 11 amps? So let's start looking in here, and we see at 2 amps for the resistor, of course the slope here, that's the resistance. But for the filament lamp here, if I look, the resistance here, I want to do a tangent line here. So a line that only crosses at this point because it's not a straight line. So a tangent line would look something like this. And if I compare the slopes of these two objects, I can see that the resistor, the slope of the resistor is larger. So I would say at 2 amps, the resistor has larger resistance. And then we can complete this again for 11 amps. And so 11 amps is somewhere around here. Again, this is the same, it's just along the line. And 11 amps for the filament lamp. Now if we draw a tangent line here, you can see this is going to be steeper. We draw a tangent line here. So now it has a steeper slope, which means a larger resistance. So at 11 amps, the lamp has more. So that's how we can use graphs to compare objects. In example 7, we have a resistor attached to a cell with a potential difference of 1.5 volts. The current is measured to be 28 amps. The cell is replaced with a new one that produces 4 volts, and then the current is 75 milliamps. And we want to determine if this is ohmic or non-ohmic. And the difference is, for ohmic, the resistance is constant. So we're looking to see if we change the potential difference, does the current change in the appropriate amount so that the resistance is the same? So for this first series, we have R is equal to V over I, which is 1.5 over 0.028, and we get 53.6 ohms. And then in the second scenario, so R2, that's going to be V2 over I2. So we're going to have 4 volts over 0.075. And we get 5.53. And we get 53.3 ohms. So I would say, based on these calculations and the measurements and the uncertainty, I would say that this is ohmic because those are very close. So the resistor is ohmic. So in summary, Ohm's law states that the electric current through a conductor between 2 points is directly proportional to the voltage across the 2 points. The slope of a VI graph is the resistance. The slope of an IV graph is 1 over the resistance. And ohmic conductors have constant resistance. So those are the most important points you need to remember from this video.